A very, very warm welcome to the today's speaker, Dr. Abhuday Mullik, Assistant Professor, Department of Chemical Engineering, Heritage Institute of Technology, and the participants of this winter internship. The topic of today's presentation is aspects of fire and explosive safety. And I am very happy to introduce my young and very sincere and vibrant, you can say, colleague, Dr. Abhuday Mullik. He has started his career in teaching not very long years before, but already he has established his mastery. Presently, the assistant professor and also the departmental coordinator of Heritage Institute of Technology. And now he is considered one of the experts in this field of chemical process safety. So the topic he has chosen is, I already told you, that aspects of fire and explosive safety. Buddha is the product of Jadavpur University. He had his bachelor's degree in chemical engineering from there. He had master's degree from Department of Chemical Engineering, University of Calcutta, and also his PhD from there. So I request Buddha to start his deliberation.
Thank you, sir. And I also thank the organizers for providing me with this opportunity, for sharing some of the information that I have with me with our young students. So without further delay, I will start the presentation. Screen touch sharing koran.
Yes.
Okay. So I think this is visible to everybody.
Yes.
So the topic of my lecture will be aspects of fire and explosive safety. Now, safety is a very important and very useful as well as very neglected aspect of the industry in our world today. But without safety, you cannot proceed with industry, especially in the chemical industry. And why is safety such an important thing? If your workplace is not safe, that means if you are constantly in fear or anxiety about what will happen if something goes wrong in your workplace, obviously that will affect your productivity. So a safe workplace ensures better productivity. Also, if the workplace is not safe, that means if the plant where you are working, it is not safe, then the quality of the product suffers because of lack of some control measures that should be there in those plants. A good safety record also boosts the image of the organization. That means if an organization suffers from accidents on a day-to-day basis, the image of that organization suffers a great deal. Hence, a good safety record also will lead to procurement of some important orders or something like that to an organization. And lastly, safety audits are nowadays a part and parcel of any industry. And whenever such a safety audit takes place, if the safety measures are not in place, then there is a last minute hurry to put everything in place, and this creates a chaos in the organization. But if you are constantly following all the safety regulations and you are complying with whatever has been set by the standard organizations, then You don't need to go for this last minute chaos before any safety audit. And all the operations in your plant will be running smoothly, and you shall come out of the safety audit with flying colors. So these are mainly why safety is so important, and safety is a vast topic. It is a specialized branch of engineering. Whenever some graduates from any engineering stream go into an industry, they are given a training on safety separately, which can last for 6 months. So you can imagine how important safety is, such that a special training is given on safety to every engineering graduate who joins an industry. So let us come to some important terms in relation to safety. The basic definition of safety has been given like this. That is, it is the prevention of accidents through the use of appropriate technologies. What these technologies are required for? They are required to identify workplace hazards and eliminate those hazards before an accident occurs. What is a hazard then? Any chemical or physical condition that has the potential to cause damage to people, property, or environment, that can be classified as a hazard. So the job of a safety engineer in a plant is to identify these hazards, and there are some specialized techniques for hazard identification. So to identify these hazards in the first place and to eliminate these hazards before an accident occurs, in totality, this is called safety. Another concept that is associated with safety is risk. Risk is the probability or likelihood of an accident or incident occurring. And it also measures the human injury, environmental damage, or economic loss in terms of this probability of the occurrence of an accident. So these are some common terms that are used in safety engineering. There are lots of other terminologies, but because we have 1.5 hours with us, we shall not go into details of those terms. We shall proceed with whatever the topic has been chosen by us. Now, hazards, as I was saying, that they are in chemical or physical conditions that have the potential to cause accidents. In an industry, hazards can be broadly classified into two types, mechanical and chemical. Now, both these types of hazards may exist in your industry. If it is a chemical industry, both these types of hazards may exist. Mechanical hazards can be as simple as tripping over something or falling off from some height or injury due to moving equipment. Chemical hazards are more important to us as of now. They can be caused because of a probability of fire and explosion, because of some uncontrolled chemical reaction, and because of some toxic elements or chemicals which can be leaked or released into the atmosphere and can cause potential damage to people, property, or environment. So fire and explosion are a chemical hazard that can occur in any type of industry, and we shall devote our attention to these fire and explosion hazards. Chiefly, what are some basic aspects regarding fires and explosions? Why are they caused? I will not go into those, because why fires and explosions happen, that is a vast topic. And there are umpteen number of reasons why fires and explosions can happen in an industry. So the content will be some information related to fires and explosions, as well as how to mitigate these fire and explosion hazards. Now, organic solvents, for example, alcohols, acetone, etc. These are very widely used in chemical industries. and they are the most common cause of fires and explosions in the industry. Fires and explosions both result in substantial losses of human life and infrastructure of the plant, but there is a distinguishing factor between a fire and an explosion. Both of them involve energy release. When something catches fire, a lot of heat energy is released, and when something explodes, again a lot of energy is released. So both of them are characterized by energy release, but they are differentiated by the rate of this release. Fires release energy slowly. You have all seen fires happening. So whenever you see something on fire, you see that the energy release is slow. But explosions, I think most of you have seen videos or experienced some explosions in television or something like that. Whenever explosions happen, a lot of energy is released within a very short time. And this makes explosions much more hazardous than fires. Fires and explosions are interconnected because fires can result from explosions, or explosions can result from fires. So both of these are connected in some way, and especially when you talk about the chemical industry, these are most often these happen side by side or one after the other in a very short time. Now, regarding fires and explosions, some terminologies are there which are going to be important. Combustion or fire is a chemical reaction where a substance combines with an oxidant and releases energy. This is known to, I think, all of you. So part of this energy that is released is sustaining that reaction, that is the combustion reaction. Ignition of a flammable mixture is caused by the mixture coming in contact with an ignition source with sufficient energy. That means ignition is the sparking or the starting of the combustion reaction. Without a source of ignition, you cannot have a combustion or a fire. So the flammable mixture, that is the mixture or the component which can catch fire, that is termed a flammable mixture or a flammable component. Whenever it comes in contact with a source of ignition, and if there is sufficient energy present, then that causes ignition of the flammable component and it catches fire. Also, there can be auto ignition. That means a gaseous component may catch fire on its own. And in general, this requires very high temperatures. So whenever some gaseous component reaches a very high temperature, then it can catch fire on its own, and this is called auto ignition. Now, flash point is another very important parameter related to fire safety. It is defined as the lowest temperature at which a liquid gives off enough vapor to form an ignitable mixture with air. And why is this so important? Because flashpoint data for fuels are required for storage and transportation of these fuels. If you don't know the flashpoint of a fuel, then if you are transporting or storing that fuel at a temperature which is above its flash point, then there is always a very high chance of that fuel to catch fire in presence of an ignition source. Another important term which is similar to flash point is called fire point, and it is a temperature at which a vapor that is given off by a liquid will continue to burn once ignited. That means there will be sustained burning of the vapor from the liquid at this temperature. So the knowledge of flash and fire points for any flammable substance is a must when you are handling these flammable substances in the industry. Now, as we have discussed, a fuel in presence of oxygen and an ignition source catches fire. And this concept is expressed in the form of a fire triangle, where, as you can see, the three sides of the triangle represent the three essential elements which are required to sustain a fire. That is oxygen, heat, and fuel. Fuel is the flammable material which will catch fire. Oxygen will help it in sustaining the combustion. That is, it will help to burn the fuel. And the burning will require energy, which will come from the ignition source. So this is called a fire triangle. And whenever all the elements of a fire triangle are present at one place in sufficient amounts, there will be a combustion or fire. Now, a modern concept has evolved which looks at fire or combustion in a different way. It views the three elements, that is oxygen, fuel, and the heat, that is the ignition source. Together, these three elements sustain the fourth element, that is the combustion or the uninhibited chemical reaction itself. This combustion reaction is being expressed as an uninhibited chemical chain reaction. So these four elements together will constitute a fire tetrahedron. So the modern concept of a fire triangle has evolved into a fire tetrahedron, where the original three elements of a fire triangle together work to sustain the fourth element, that is the uninhibited chain reaction, which is nothing but the fire. Now, there are some common examples of fuels, oxidizers, and ignition sources. For example, liquid fuels are very common: gasoline, ether, acetone, alcohols, etc. Organic solvents are very, very flammable, and they are classed as liquid fuels. There are also solid fuels, solids which can catch fire, like plastics, wood dust, metal particles, fiber, etc. And gases which are highly flammable, like propane, hydrogen, carbon monoxide, acetylene, and there are other such gases. Oxidizers which help in burning are, there are gaseous oxidizers like oxygen itself, also fluorine, chlorine, etc. Liquids that can act as oxidizers are hydrogen peroxide, perchloric acid, nitric acid, etc. Solids which can act as oxidizers are metal peroxides like sodium peroxide, potassium peroxide, ammonium nitrites, etc. These can cause oxidation or combustion of a fuel. Ignition sources, they can be of various types like sparks, flames, static electricity, a large amount of heat. All of these may trigger ignition of a flammable substance. Now, when we come to fire and flammability, there is a very important concept called flammability limit. Now, if you have a fuel in a mixture with air or oxygen, and if you have an ignition source, it is not always that there will be fire. The fuel has to be present in a specified proportion with air or oxygen for fire to happen. Too much fuel in air or oxygen will not catch fire. Too little fuel, again, in air or oxygen will not catch fire in spite of the presence of an ignition source. There is an upper limit and there is a lower limit of the percentage of fuel in air or oxygen which can catch fire. These are called the upper flammability limits and the lower flammability limit. They are defined as, the lower limit is defined as the minimum concentration of flammable vapor in air which can be ignited by an ignition source. For example, in the figure that is given in the bottom of the slide, you can see that natural gas, its flammability limit, the lower limit is 5% by volume in air, and the upper flammability limit, as you can see, is 15% by volume in air. That means if natural gas is present, natural gas vapor is present in air at a volume percent less than 5, that means suppose 3.5% by volume, even on the presence of an ignition source, that mixture with air will not catch fire. Also, if natural gas vapor is present in air in a very large quantity, suppose 25% by volume, then also if you light a match in that mixture will not catch fire. So these limits determine the range of flammability of any particular fuel. The mixture of the fuel with the oxidizer, that is air or oxygen, is flammable only when the composition is between the lower flammability limit and the upper flammability limit. And typically these lower flammability limit and upper flammability limit are expressed as percent by volume of the fuel in the mixture with air or oxygen. And we have seen, the experiments have seen that the upper flammability limit increases with temperature and the lower flammability limit decreases with temperature. Why these things happen? Because why too little or too much fuel doesn't catch fire? This is again a subject of thermodynamics, and there is a lot of intricate detail thermodynamics behind this. Now, as an engineer, you may be asked or you may be involved in finding out the flammability limit of a particular fuel air or fuel oxygen mixture. Suppose you have a mixture of propane with air and you were to calculate, or a mixture of propane, hydrogen, carbon monoxide with air, that is a mixture of 3 flammable gases with air, and you are to calculate the lower flammability limit and the upper flammability limit of this mixture. Because suppose such a mixture is going to come out of the stack of your factory, and as a safety engineer, you are to calculate these flammability limits of the mixture that is coming out of the stack. Then the equations that can be used are called the Le Chatelier equations. The mixture lower flammability limit is given by the reciprocal of sigma I is equal to 1 to n yi by LFLI. LFLI is the lower flammability limit for the ith component in the mixture. Yi is the mole fraction of the ith component of the mixture in a combustible basis, and this is very important. Yi is the mole fraction of the component I, that is the fuel ith fuel, on a combustible basis. And N is the number of combustible species. Suppose, as the example that I was talking about, we have a mixture of 1.5% propane, 2% hydrogen, and 1.5% carbon monoxide in air. So the total combustible percentage is 1.5 plus 2 plus 1.5. That is 5%. So the mole fraction of each of these combustible components will be calculated on the basis of that 5% total combustibles. That is, if you want to calculate the mole fraction of hydrogen, then it will be 2 by 5. If you want to calculate the mole fraction of propane, then it will be 1.5 by 5, not 1.5 by 100 or 2 by 100. The mole fraction in this equation has to be calculated taking the basis as the combustible substances and not the total mixture. Similarly, the upper flammability limit of the mixture is given by a similar equation, and these equations can be used for estimating these lower and upper flammability limits for a mixture of combustible substances with air. For many hydrocarbon vapors, these limits can be estimated without experimental data. Because here in the La Chatelier equations, the lower limits and the upper limits of the individual components, that is the LFLI and the UFLI, those have to be found out from experiments or from tabulated data, literature. In the literature, there are tables which give the values of the lower and the upper flammability limits for many combustible substances. And these have been calculated by experimentation. Without experimentation also, you can estimate the lower and upper flammability limit for many hydrocarbon vapors using stoichiometry. The lower flammability limit can be expressed as 0.55 of CST, and upper flammability limit can be expressed as 3.5 times the CST, where CST is the stoichiometric concentration of the fuel required for combustion. For estimating or calculating CST, you have to write the equation of combustion for that particular fuel, and you have to calculate the value of this stoichiometric concentration with respect to the total amount of oxygen that you have in your combustion reaction. And when you have got the value of CST, that is the stoichiometric concentration, you can estimate the LFL and the UFL for that particular fuel using these simple equations. Now let us come to some facts about explosions. Now, an explosion is a rapid expansion of gases, resulting in a rapidly moving pressure or shock wave. That is, when something explodes, the gas or the air near it rapidly expands. And this compresses the surrounding air, which propagates via a pressure wave. This compression wave propagates through the air, and this is called a pressure or a shock wave. The explosion can be mechanical, that is by a rupture of a pressure vessel, or it can be the result of a rapid, uncontrolled chemical reaction. Whenever a chemical reaction becomes very rapid, the rate of the chemical reaction becomes uncontrolled, or it becomes a runaway reaction, the contents of the reactor may explode. And when the explosion happens, the air near it gets compressed, and this compressed air is propagated through the surrounding as a shock wave, as you can see in this figure. Now, when some substance explodes, there also the concept of this lower limit and the upper limit comes. Ordinarily, a combustible substance can also explode, and the lower flammability limit of that combustible substance is also the lower explosion limit of that substance. And correspondingly, the upper flammability limit of that substance is also the upper explosion limit of that substance. That means if you have, for example, hydrogen, the lower flammability limit of hydrogen can also be substituted by the lower explosion limit of hydrogen, and the UFL of hydrogen can be substituted by the UEL of hydrogen. That means these can be used interchangeably. Now, as I have said, the shock wave that is produced, it is an abrupt pressure wave that moves through a gas. If this explosion happens in open air, that is in an unconfined space, then the shock wave is followed by a strong blast of wind. And this combination of the shock wave and wind is called a blast wave. And this is a characteristic of any explosion that happens outdoors, that is in an unconfined area. Now, there are many types of explosions that are defined in safety engineering. Mechanical explosions are explosions resulting from the sudden failure of a vessel containing a high pressure non-reactive gas. Suppose you have nitrogen gas inside a cylinder at a very high pressure. And suppose the sealing of that cylinder, that is the mechanism which keeps the cylinder sealed, fails, and for some reason or the other, the pressure inside the cylinder starts rising. Then that cylinder, after it reaches the maximum pressure that it can withstand, that cylinder will burst, and that will be a mechanical explosion. Secondly, deflagration. This is an explosion in which the reaction front, what is the reaction front? Commonly, explosions are the result of some rapid combustion reactions. The reaction front is the area or the energy carrying area from the reaction. That is the surrounding air or atmosphere that carries the energy of the reaction with it. That is the reaction front. And it moves outwards from the center of the explosion. And this reaction front compresses the air surrounding it, which results in the propagation of the pressure wave. Hence, in any explosion, from the center of the explosion, there are two things propagating outwards. One is the reaction front, one is the shock wave or the pressure wave. And the pressure wave of the shock wave is created by the reaction front. And after it is created by the reaction front also moves outwards from the center, as well as the shock wave also moves outwards from the center of the explosion. Now, deflagration is an explosion in which the reaction front moves at a speed less than the speed of sound in the unreacted medium. That means when there was no reaction, that is no combustion, normal atmospheric condition, the speed of the sound in that atmospheric condition has some value. When the explosion takes place, the reaction front, if it moves with a speed less than that speed of sound, then it is called a deflagration. And detonation is an explosion in which the reaction front moves at a speed greater than the speed of sound in the unreacted medium. Confined explosions are explosions that occur within confined spaces. That means either within a vessel or within a building. And unconfined explosions are those which occur in the open, outside. And unconfined explosions generally occur because of release of flammable gases. When these flammable gases are released from their tanks due to some leakage or something, some failure, these flammable gases, whenever they reach the explosive limits, in presence of some ignition source, they can explode. A special type of explosion is called a boiling liquid expanding vapor explosion, or a BLIVE. This I will come in details in the subsequent slides. It occurs when a vessel that contains a flammable liquid at a temperature above its boiling point, if that vessel ruptures, then a BLIVE occurs. How does it occur? I will discuss in details in subsequent slides. And there is a particular type of very dangerous explosion in industry, that is dust explosion. And this explosion results from the rapid combustion of fine solid particles. In many industries, we have to work with fine solid particles. And these fine particles of solids are often very, very combustible. And if there is a rapid combustion of these fine solid particles, there is an explosion which is called dust explosion. And this is very, very fatal. Now, as I have said, an explosion releases a tremendous amount of energy in a very short time. And how do we quantify the energy that is released? This is generally quantified in terms of TNT equivalency. You may have heard of atomic bomb explosions or any energy release like that of a meteorite impact or something like that, of an earthquake, etc. Any release of energy is quantified in terms of TNT equivalency, that is equivalent to 1000 megatons of TNT, 500 megatons of TNT, 4 gigatons of TNT. What is this actually? This is actually a quantification of the release of energy. And the assumption for this is that any exploding fuel behaves like exploding TNT on an equivalent energy basis. And the logic of calculation is how much TNT would have produced the same explosion energy as the explosive fuel in question. Suppose, for example, you have a LPG Horton sphere or a spherical pressure vessel which contains LPG, and that bursts and the LPG explodes, releases some amount of energy. So my question will be, how much TNT would have been required to produce the same amount of energy as released by that LPG? That will be called the TNT equivalent of that explosion. And the equation of TNT equivalency is given by this equation. Now here, mTNT is the equivalent mass of TNT that is needed for achieving the same explosion energy. M is the mass of the combustible or explosive fuel that has exploded. Del HC is the explosion energy per unit mass of the fuel. ETNT is the explosion energy of TNT. That is the explosion energy if unit mass of TNT explodes. And that has a standard value, 4686 kilojoule for 1 kg of TNT. Epsilon is a parameter here which signifies the efficiency of that explosion. And for explosions that happen in our industry, this epsilon value generally lies between 1% and 10%. So using this equation, you can calculate the equivalent mass of TNT that would have produced the same amount of energy as the explosion that occurred in your plant. This is how you can measure or quantify the energy released by an explosion. Now, we were talking about detonation and deflagration. Let us see their differences in more details. In some reactions, rapid combustion reactions, the reaction front is propagated by a strong pressure wave, which compresses the unreacted mixture in front of the reaction front above its autoignition temperature, and this compression occurs rapidly, resulting in an abrupt pressure change or shock in front of the reaction front. If you can see in this figure, the black bar is the reaction front and the gray bar is the shock wave or the shock front. The reaction front is propagated by a pressure wave, and because of this reaction front, the pressure wave that propagates ahead of it, it compresses the air or the unreacted mixture ahead above its autoignition temperature, and this compression occurs rapidly. Whenever the compression happens, that is the unreacted area ahead of this reaction front is compressed above its autoignition temperature, that also explodes. In this way, there is a propagation of the reaction front. And when this compression of the unreacted mixture ahead of the original reaction front occurs abruptly or rapidly, then there is a very abrupt pressure change in front of the reaction front. And this is denoted by this narrow overpressure graph. Very abrupt pressure change. That means a spike in the pressure over a very short distance. That is an abrupt increase in pressure. This is the characteristic of a detonation explosion. And for deflagration, what happens is the energy from the reaction front is transferred to the unreacted mixture ahead of the reaction front, generally by molecular diffusion or by heat diffusion or heat conduction. And because these diffusive processes are very slow, the reaction front propagates at a very slow speed. That is a speed less than the speed of the sound. And there is in front of the reaction front, the compression of the unreacted zone is not that abrupt. And the rise in pressure happens gradually over a large distance. As you can see, the curve is a flatter curve. The pressure variation with the distance is flat compared to detonation, where the pressure variation is very abrupt. Suddenly the pressure increases, and this continues over the distance through which the explosion spreads. So detonations carry a lot more energy and cause a lot more damage than deflagrations. Now, as we are discussing about BLEVE, let us come to this. What is a boiling liquid expanding vapor explosion? This type of explosion occurs if a tank containing a volatile liquid is a liquid which has a very low boiling point. That is, it is prone to get vaporized very quickly, and volatile liquids are generally very combustible or flammable. So if a tank containing a volatile liquid, by chance, if it gets heated by an external source, maybe a fire that is occurring near the tank heats up. And because of the heating up of the tank, the vapor pressure of the liquid inside the tank increases. The tank becomes structurally weak due to heating. There is a thermal degradation of the tank material. And after it weakens to a significant amount, that tank may rupture and release the volatile liquid. And whenever this volatile liquid gets released to the atmosphere, it starts boiling immediately and rapidly vaporizes. This vaporization creates a vapor cloud which explodes. And this is called a boiling liquid expanding vapor explosion. What are the steps that occur in a BLEVE? The first requirement is some sort of heat source need to be there. That is, if a tank is storing a volatile liquid, a fire can develop adjacent to the tank. What the fire will do is the fire will heat up the walls of the tank. Now, if the tank is partially filled with the liquid, then what happens is the tank wall, that is the portion of the tank wall which is below the liquid level, gets cooled by the liquid. That is, the liquid absorbs the heat from the tank wall, cools down the tank wall, but itself gets heated. And thereby the vapor pressure inside the tank increases. The portion of the wall above the liquid level in the tank cannot be cooled down by the liquid, hence the temperature of that portion goes on increasing. Now, suppose the flames of the fire reach the tank wall where there is no liquid, that is, there is only vapor. Then the temperature of the metal of the tank rises in that portion where there is no liquid to cool it down, and ultimately there some thermal stresses develop which cause ruptures in the tank. Once this rupturing starts, the tank completely breaks apart, releasing the volatile, highly volatile boiling liquid, and that liquid immediately forms a vapor cloud which explodes in contact with atmospheric oxygen. Now, what we have here is a video of a BLEVE. This is a short 2-minute video. You can see what happens when a BLEVE occurs. So I guess you have now known the scale on which such an explosion happens. Now, this part was about some aspects that are related to fire and explosion hazards. Now we come to how can we mitigate fire and explosion hazards. Now, fire triangle, the concept of a fire triangle is very important here. As we know, all the three elements of a fire triangle need to be present side by side for a fire to occur. So a strategy for mitigation of fire and explosion hazard is if we can prevent any one of these elements from being in contact with the other elements, then we can prevent a fire. So we can prevent flammable mixtures. We can prevent the ignition, that is the initiation of the fire or explosion. Or if for some reason a fire and explosion has happened, we can minimize the damage afterwards. So if any of the sides of the fire triangle is eliminated, either the fuel or the oxygens or the ignition source, then we can prevent a fire or an explosion. One very widely practiced procedure for preventing fire hazards in industry is called inerting. This is the process of adding an inert gas to a combustible mixture to reduce the effective concentration of oxygen below the limiting oxygen concentration or LOC. The limiting oxygen concentration is the minimum oxygen concentration required for sustaining the combustion reaction. So if I introduce an inert gas into the system, the partial pressure of oxygen decreases. And because of this, if there is enough inert gas, then the concentration of oxygen can come down below the LOC. And this will be called inerting. As inert gases, generally nitrogen, carbon dioxide, or steam are used. Now, what we do in inerting is, suppose we have a vessel with a combustible substance inside. We initially purge the vessel with an inert gas to bring the oxygen concentration down to a safe limit. And what is considered safe is generally 4% below the limiting oxygen concentration. That means if for a particular combustible substance, the limiting oxygen concentration is 10% by volume, we want to reduce the concentration of oxygen by inerting to about 6% by volume. So this is done by purging the vessel or filling up the vessel with an inert gas. Now, after the empty vessel has been inerted, then we charge the flammable material into the vessel. That means if we have a storage tank which is supposed to contain ethylene. Now, ethylene is a flammable substance. Now, if I want to directly charge ethylene to the storage tank, there might be a source of ignition due to some friction or something else, which can cause explosion or combustion of the ethylene. If I don't inert this storage tank previously. If I purge this storage tank, this empty storage tank with nitrogen or carbon dioxide beforehand, then what will happen is the concentration of oxygen inside the storage tank that was there previously will be reduced drastically so that after inerting, I can safely pour the combustible ethylene into the tank. Now, the inerting system generally consists of a regulator which is connected to the cylinder containing the inert gas. And this regulator is designed to maintain a fixed positive pressure of the inert gas inside the vessel, which is to be inerted. And why always a positive inert gas pressure is maintained inside the vessel? So that we want to ensure that inert gas is always flowing out of the vessel. And this will prevent leakage of outside air into the vessel. So if I want my reactor or my storage tank to be completely inerted always, what I do is generally I connect the storage tank or the reactor with a nitrogen cylinder or a carbon dioxide cylinder or any inert gas cylinder. And the transfer line of this cylinder is provided with a regulator, which will be set to such a point so that there is always a positive pressure of inert gas within the reactor or the storage vessel. So that the pressure of the inert gas inside the storage vessel is higher always than the outside pressure. So that there is always a flow of inert gas from the vessel to the surroundings and not a flow of air from the surroundings to the vessel. Apart from this, there are also automatic inerting systems with an analyzer, which continuously monitors the oxygen concentration inside the storage vessel or the reaction vessel. The former case where we have only a regulator, what we do is we continuously keep the flow of the inert gas on. And there may be a lot of inert gas which is not required in that much amount, but we don't have a control over it. But if we have an automatic inerting system with an analyzer, what the analyzer does is it continuously monitors the concentration of oxygen gas inside the storage vessel or the reaction vessel and sends a feedback to the automatic controller. This controller regulates the flow of the inert gas accordingly, and this saves on the inert gas cost. Now, what are the purging techniques that are used for inerting? The foremost technique that is most commonly used is vacuum purging. And this is the most common procedure used for reactors. When you need to maintain an inert atmosphere for a reaction to occur inside a reactor, the most common procedure that is used for reactors is vacuum purging. What we do is we connect the reactor with some vacuum device and we achieve the desired vacuum in the reactor at first. That means we suck out all the air that may be present within the reactor and we achieve the desired vacuum level. Then, because we cannot carry out the reaction in the vacuum, we need to again repressurize this reactor, but not with air, but with an inert gas. That means then we relieve the vacuum by introducing inert gas up to the desired oxidant pressure. For example, if you have a reactor vessel which has originally is at 1 atmospheric pressure, when you connect the vacuum pump to that, suppose you have a vacuum up to 200 millimeter mercury. Then after you have achieved this vacuum, what you do is you then transfer some amount of inert gas into the reactor vessel so that the pressure again rises from 200 millimeter mercury up to the desired pressure, which is safe for my chemical reaction to occur. So this is vacuum purging. The opposite of vacuum purging is pressure purging, and vessels can be purged by adding inert gas under pressure. That is, you can transfer inert gas under high pressure from a cylinder into the vessel. And after the gas is transferred to the vessel, this gas is diffused throughout the vessel, and lastly, it is vented to the atmosphere, usually down to atmospheric pressure. That means you continuously transfer a high pressure inert gas into the vessel, diffuse the inert gas throughout the vessel, then take it out of the vessel. And this is continued until the desired concentration of the oxidant inside the vessel is reached. The third method of purging is called sweep-through purging. That is, it adds the inert gas into a vessel at one opening and withdraws the gas mixed with oxygen from another opening to the atmosphere. And this occurs, the total process occurs at atmospheric pressure. That means there are two openings in such a vessel. Through one opening, we are adding inert gas. This gas mixes with the oxygen or air that may be trapped inside the vessel. And this mixture is withdrawn from the other opening and vented to the atmosphere. This is called sweep-through purging. The fourth method is siphon purging. This involves filling up the vessel with a suitable liquid. You completely fill up the vessel with liquid. Then by siphoning action, the liquid is drained out from the vessel. And when the liquid level drops, in the vapor space above the liquid level, you add simultaneously the inert gas. Because of the siphoning action, the liquid is drawn out of the vessel, and this movement of the liquid out of the vessel draws in the inert gas.
சரி நமக்கு கிளம்பும் தப்பு நாங்களும் அதே நிலைமைதாங்க.
So let us then come to the application of the flammability diagram for inerting. Flammability diagrams are triangular diagrams which represent the interaction between the three elements that is a fuel, oxygen, and the inert gas. As you can see in this diagram, the flammability zone is estimated and it is demarcated in this diagram. As you can see, this is the flammability zone. This line is the upper flammability limit and this line is the lower flammability limit. Now, when there is an empty vessel or there is a vessel filled with something and you want to take that vessel out of service, that is, you want to empty that vessel. There is some flammable material inside the vessel and you want to empty that vessel, that is you want to take that vessel out of service. This will be achieved by an inerting procedure, and for correctly implementing this inerting procedure, you need to take help of the flammability diagram. The vertex at the top represents 100% fuel. The line at the bottom represents pure air. This point represents pure air, which has 79% nitrogen. And once we introduce air for purging, if you introduce air for purging, the composition of the flammable substance in the vessel will follow this air line up to this point. As you can see, this will pass through the flammable zone. That means there is a chance at some concentration of the air inside the vessel, there may be flammability hazards. So what to do is we need to purge the vessel with an inert gas. When we purge the vessel with an inert gas, the composition of the flammable substance inside the vessel will start from here and follow this side of the triangle. And if we want to optimize our inerting procedure, what we can do is we can estimate the point of intersection between this stoichiometric line and the lower flammability limit, which is here. We can connect the pure air composition with this point and extend it up to the fuel side. What we can do is we can use nitrogen purging up to this concentration of fuel. Then we can use air purging where the fuel composition will follow this line and ultimately come to the pure air composition, so that we can avoid coming into the flammable zone. And this composition of the fuel up to which we can allow nitrogen purging is called OSFC, or the out of service fuel concentration. So how can we use it? We can first determine the point of intersection of the stoichiometric line and the lower flammability limit. We can connect the pure air point, that is this 79, this axis on the nitrogen axis is 79, with this point of intersection and extend it to the fuel side or the fuel arm. Now what we can do is we can use nitrogen purging. When you introduce nitrogen inside the vessel, the flammable substance concentration will follow, the change of the concentration will follow this fuel line. Up to this OSFC concentration, you can use nitrogen purging. Then you can switch to air purging, where the fuel concentration path will follow this line up to the pure air point. And we are avoiding this flammable zone. Flammability diagrams are available for many fuels. So for the fuel in question, you can get hold of such a flammability diagram. You can determine the OSFC, and accordingly, you can purge nitrogen up to the OSFC concentration. Then you can purge air, because that will save on nitrogen gas cost. Another important source of ignition that can lead to a devastating fire or an explosion is static electricity. This is a very dangerous thing in the industry because we cannot see it. And this is a very, very common ignition source within a chemical plant. There are lots of processes which result in building up of static charge. And whenever such a static buildup discharges, there is a spark, and this spark acts as the ignition source. If by chance a flammable substance is present near the spark, then that flammable substance can catch fire or it can explode. Whenever in a plant there is inevitable buildup of static charge, we have to design the plant equipment in such a way that continuously the static charge can be dissipated and the atmosphere around the regions where static charge is generated are always kept inert. Industrial examples which are very common and which commonly give rise to accumulation of static charge are, for example, when you pump a non-conductive liquid through a pipe. The friction of the liquid with the pipeline gives rise to the static charge buildup. If you mix immiscible liquids, there also is a lot of shear or friction between these two immiscible phases, which can lead to buildup of static charge. When you convey fine powders of solids through pipelines by pneumatic conveying, the friction of the solid with the pipelines can give rise to static charge buildup. So all these are examples, very common examples. We do these processes regularly in industry, and these processes are associated with a propensity or tendency for static charge buildup. Now, if in our plant, there is a possibility of presence of flammable vapors, standard safety engineering suggests that any charge accumulation exceeding 0.1 millijoule is dangerous. See, such a small amount of charge, any charge accumulation exceeding 0.1 millijoule, it is considered dangerous. So what can be done for preventing electrostatic ignitions? What we can do is we can reduce the rate of charge generation by implementing some measures. And also we can increase the rate of charge relaxation, that is dissipation of the charge from where it accumulates to other places. We can also design some systems which can discharge this accumulated static charge by means of low energy discharges that are safe. And these are some special designs that are generally implemented for powder handling systems. Now, in some cases, it happens that we cannot entirely eliminate dangerous discharges. Then what we can do is we let the discharge happen, but we don't let the discharge give rise to a fire. How? By maintaining oxygen levels or oxidant levels below the combustible levels, that is by inerting, or by maintaining the combustible levels below the LFL or above the UFL. That is, whenever there is a process or an equipment where we know that there is going to be a dangerous discharge and we cannot do anything about it, what we can do is we can let that happen, but we can take other preventive measures. That is, we can maintain the oxidant concentrations below the combustible levels by inerting, or we can take care to maintain the fuel levels below the LFL or above the UFL. So that in spite of the presence of that discharge or ignition source, because the other two arms of the fire triangle are being eliminated, the chance of a fire is going down. These two are common methods for eliminating dangers because of static buildup: bonding and grounding. As you can see in the figure, if two materials are conductive, then the voltage difference between these two conductive materials is always kept zero by bonding these materials. That is, I bond one end of a conducting wire to one of these materials and the other end to the second material. For example, you can see in this figure, left-hand side figure, there is a vessel which has a agitator inside, and there is a pump which is pumping something inside the vessel. Now we have this vessel is made of metal and this pump is also made of a metal. So these metals, because they may be at different voltages, because of the difference in voltage between these two equipment, there can be a discharge of static electricity. But we don't let that happen. How? We connect a conducting wire between these two materials so that the material where the voltage accumulation is high or the static charge accumulation is high, that charge will go through the conducting wire and ultimately there will be a charge equilibrium. Grounding is when sets of bonded materials, that is materials which are bonded, that is which have undergone bonding, these sets of materials may have different voltages. For example, look at this figure on the right hand side. This horizontal tank is being filled up by this vertical container. Some liquid is there in this vertical container and this is being transferred to the horizontal tank. This tank is bonded and this vertical container is also bonded separately. But the voltage in this bonded tank and the voltage in this vertical container may be different. This voltage difference can be reduced to zero if we connect this horizontal container to the ground or earth. That is called grounding. Bonding and grounding, what they do is they reduce the voltage of an entire system to ground level or zero voltage. And because of this, the charge buildup in any place where there is bonding or grounding, the charge buildup is eliminated. And hence static sparks can be eliminated if you bond and ground your conducting piece of equipment. A special care has to be taken when you want to fill up a tank or a container with liquid. Because whenever you fill up a liquid into a tank, if you just pour the liquid down the tank, the liquid will splash on the bottom of the tank and this splashing will create a lot of friction. And because of it, some static charge may accumulate. If that liquid or if something is flammable inside the tank, then the static charge may lead to a fire. So the common practice in industry is to use deep pipes or angle irons for charging a container with liquid. Charging means filling up a container. Whenever you want to charge a container, an empty container with liquid, you use deep pipes or angle iron. Now, deep pipes are a pipe like this, which goes down almost to the bottom of the liquid vessel. The liquid is transferred through the deep pipes, and the liquid comes out of the deep pipe just before striking the bottom of the vessel. And because the height difference between the bottom of the deep pipe and the vessel bottom is not that much, the splashing is reduced. Hence, the friction is reduced and charge buildup reduces. Now, whenever you stop the inlet flow, there may be a chance for back siphoning of the liquid that is charged through the deep pipe. And in order to prevent this, always there is a hole that is kept at the top of the deep pipe for breaking the siphoning action. Another alternative is to use a rod like this, which is called an angle iron. That is, the charging pipe is not that much deep. It is shallow, that is just enters the vessel entry point, and the liquid from the charging pipe is allowed to flow down the side of the angle iron slowly. It trickles down the side of the angle iron and fills up the tank. And because it trickles down the side of the angle iron, there is no splashing and no static charge buildup. These are two techniques which are always used in industry for charging any empty container with a liquid. And these procedures are told to the new recruited engineers when as a part of their safety training. That is, whenever you are going to charge an empty container, always use deep pipes or angle irons, and always make sure that the container is bonded or grounded. All these have to be made sure before the engineer goes to charge the container. So these are taught as parts of safety training. Another thing which can reduce charge accumulation are some chemical additives which are called anti-static additives. These are generally non-conducting organic materials, and what they do is they increase the electrical conductivity of these non-conducting organic materials. If the organic materials that are non-conducting, if charge builds up on them, because they are non-conducting, that charge continues to accumulate over time and ultimately can lead to a discharge or a spark. Now, if you can increase the conductivity of these non-conducting materials, then the charge dissipation can be made easier. And this is done by adding some chemicals which are called anti-static additives. For example, are water and polar solvents like alcohols. And these additives must be soluble in the non-conducting liquid, because again, insoluble phases can lead to static charge generation because of friction. So the additive that you are going to add to increase the conductivity of this non-conducting liquid should be soluble or miscible with this non-conducting liquid. A very widely used and very effective method of preventing fire and explosion is ventilation. Proper ventilation can mitigate the fire and explosion hazard to a large extent. What ventilation does is it dilutes the explosive vapors with air to prevent explosion, or it can confine the hazardous flammable mixtures in one place. Open air plants are recommended because the wind velocities are high enough so that they carry away or dilute any volatile chemical leaks that may happen within a plant. You cannot see a chemical vapor leaking. You may have ethylene or propylene or propane vapors accumulated in the space inside a vessel or inside a building, but you cannot see it. Now, if it is exposed to atmosphere, what can happen is the flowing wind can carry these leaked vapors out from that place and does not allow these vapors to accumulate at one place, so that the concentration of these vapors cannot fall into the flammability region. And for units inside buildings, that is, if you have any factory or any reactor inside a building, You can use either a local ventilation system or a dilution ventilation system. This photograph here shows a local ventilation system where there are hoods which suck the vapors of the chemicals that can be leaked inside the room. And these vapors are carried with the air that is sucked by the fan here and ventilated to a safe place. Dilution ventilation is when the ventilation system allows a large quantity of air inside the room so that the concentration of the flammable substance inside the room is reduced. That is, it becomes diluted. So that is the function of dilution ventilation. Local ventilation carries away the flammable vapors and deposits them to a safe place. Dilution ventilation, what it does is it allows a lot of outside air to come in and dilutes the flammable substance concentration that has accumulated inside the building. So any one of these two systems can be used for proper ventilation of a unit that is housed inside a building. For mitigation of fires, we also have sprinkler systems that are widely used in a chemical plant. The sprinkler systems can be of two types, wet pipe system and deluge system. The wet pipe system is where the sprinkler heads are in the photograph you can see from where the water comes out. Those are called the sprinkler heads. The sprinkler heads are activated individually by the melting of some fusible link or a fusible plug that is there in the head assembly. That is, if the fire is there or a source of heat is there, then that heat will melt the plug that is stopping the water from coming out of the head. And the material will be designed in such a way that it will melt at a particular temperature. That means when the fire is there, the temperature inside the room will be above that temperature and the plug will melt, causing water to come out from the sprinkler heads. This type of system is commonly used in small areas, like in storage areas, in laboratories, or in control rooms, etc. Deluge systems are used in large processing units or where the actual processing equipment are there. Now, deluge systems consist of an array of sprinklers which are activated from a common control center, generally the distributed control system or the DCS system. Now, this sprinkler array is activated from this common control center that is connected with the heat or the smoke detectors. If a detector detects anything abnormal, that is a temperature rise or a smoke, then this sends a signal to the control system and the control system activates all the sprinklers all at a time. Even in areas which are not affected by the fire, there also the sprinklers will be actuated. And this is called a deluge system. And this is common where the processing areas in the plant are. Now, fire extinguishers, these we all know, are the first-hand control measures against spreading of fires. Now, fire extinguishers are classified into different types according to the fires on which they can be used. As you can see, there are these 6 classes of fire: A, B, C, D, electrical, and F. Class A fires are fires due to the burning of organic materials like paper and coal, which is a common type of fire. Class B fire is the fire that results from burning of flammable liquids like petrol, paints, solvents, etc. Class C fires are fires which result from burning of flammable gases like methane, propane, butane, etc. Class D fires are fires that result from burning of flammable metals. Electrical class E fires are electrical fires, that is fires that result from electrical equipment. And class F fires are fires when cooking oils burn, like olive oil, fat, sunflower oil, or any of these oil. When they are burnt, those are class F fires. And these charts are available, which help you in selecting the type of fire extinguisher depending on the cause of your fire. For example, you can see you can use the water type fire extinguisher only for class A fires. You can use the dry chemical powder type or the DCP type fire extinguisher for class A, B, C, D, E. Almost all the classes of fires can be effectively extinguished by this dry chemical powder fire extinguisher. Cooking oil fires can be extinguished by wet chemical type fire extinguisher. Like these charts, these are also taught, or these are also shared with new recruits for safety training, that how to operate fire extinguishers and which type of fire extinguishers to select for which kind of fire. Now, the last portion of my discussion will be the prevention of dust explosions. As I have said, dust explosion is a very, very dangerous type of explosion that occurs in industries which commonly handle fine solid powders. Now, fine solids dust is not the common household dust that we all talk about. That is not the dust that is being talked about here. Dust in industry, this means fine solids. And usually, in case of dust explosions, these solids are metals. These solids are flammable and they have flammability limits which are similar to flammable gases. They can burn and they can explode also as deflagrations or detonations. Now, a very dangerous aspect of dust explosion is that primary explosions will occur. The dust will explode if it comes in contact with some in ignition source and if the concentrations are within the flammable regions. This is the primary explosion. But in case of a dust explosion, these primary explosions will initiate secondary explosions. How? Because the force or the turbulence from the primary explosion will disperse any dust that may have accumulated on the floors, inside ducts or pipelines, or above ceilings, etc. Those dusts will also be dispersed by the turbulence caused by the primary explosion, and they will again in turn undergo explosion. So the explosion spreads rapidly, and this creates its danger. Now, flammable dusts have, or they follow the fire pentagon, not the fire triangle, not the fire tetrahedron, but the fire pentagon. What? Fuel, that is the dust, ignition source, oxygen. The other two factors that lead to dust explosions are low moisture, that is dryness, and if the dusts are suspended in air. Ordinarily, if dust is accumulated on some surface, you ignite that dust will burn slowly. But if the dust is as a suspension, is floating in air as a suspension, they will explode and release a lot of energy. So the low moisture and suspension in air, these are extremely dangerous conditions for a dust explosion. And in order to transfer dusts, that is fine solids or metals, into flammable liquids, requires appropriate containment. That is, the entire procedure needs to be contained in some appropriate containment area, and the entire procedure needs to be inerted. Ignition sources that can lead to dust explosions are tramp metals. That is some impurity or some outside piece of metal that has by chance come into the dust. That is, you are working with, suppose, coal dust, and by chance some iron particle has come into the coal dust. That will be called a tramp metal. And that may ignite the dust by friction with the walls of the container. You can prevent this sort of thing from happening if you have a magnetic metal collector before you convey the dust or handle the dust. This magnetic collector will remove any magnetic piece of metal from the dust. Mechanical failure can also be a source of ignition. Overheating of the dust can be a source of ignition. In this case, you need to prevent exposure to heat for prolonged periods of time. Sparks can be a source of ignition. High dust concentrations. You cannot allow dust to be accumulated in high concentrations anywhere inside a factory. Static charge buildup can lead to sparks and dust explosions. And already you know how to prevent static charge buildup by bonding and grounding. So any material or any equipment that is used for handling or conveying these solid dusts should be properly bonded and grounded. Lastly, ventilation systems must be there so that these dust explosions don't occur. Ventilations can prevent high concentration of dust from accumulation by venting out some of the dust in a safe place. So this is all that I had to share with you today. As the message suggests here, don't let your future go up in smoke. You can always follow fire safety, because in history as well as also in modern times, lots of accidents have happened. Many precious lives have been claimed. Billions of dollars or rupees have been lost because some simple safety rules were not followed. So I will urge all of the audience to please follow all the things that have been discussed. Fire safety, there are a lot of other things, but this is a vast subject, as I had said, and the time is limited. So I only discussed about these topics in today's presentation. Thank you.
Any discussion on this particular topic? Participants? Anyone wants to have any query?
If anyone has any query, he or she may please come up with it.
We got a very important and effective presentation. In fact, the subject area is covered so nicely that I think that whatever the queries are supposed to be, that has been dispelled. So we are very much thankful to Dr. Mollik. Our next speaker is Dr. Devalina Sengupta. Devalina has got a lot of ornamental positions she is having. But since you see, this is a program between Jadavpur University and our Vivekananda Institute of Environment Management, and we are very proud that Devalina, like Abhuday is also our alumnus, the Jadavpur University alumnus, and Devalina is the alumna of Jadavpur University, a very, very prominent alumna. Presently, she is Associated Director, TEES Gas and Fuel Research Center, Water Energy Food Nexus Coordinator, Texas A&M Energy Institute. And what is a very remarkable thing, that you see that it is just the evening is approaching, and to her it is almost like early morning. Early morning means that's a cold place. So I am feeling very shaky that still she is having so much interest that she has agreed to deliver the presentation. The last program what we had, that is the National Symposium, there I have found that when she left the meeting, that time as per their American timing, it was around 3 o'clock in the night. So you can understand how much she is keen about the academic association. So I request Devolina I just read out our designation, etc. But I request Devolina to project herself so that the other participants will also be elated by seeing such a proud alumna of Jalapur University. Over to Devolina, please.
Thank you so much. To me, the only designation is that I'm a Jadavpur University alumni, and that matters the most for everything that I do, because that is what has prepared me for everything that I'm able to do in life. So I'm really thankful for Jadavpur University and for this presentation. Are you able to hear me well?
Oh, surely.
Yeah. So
Surely it's
can I?
quite audible.
Yeah.
I'm telling my coordinator to share the screen. No?
Okay. Yeah, I
Yes.
think I have.
Yes.
Yeah. Let
You
me
have
see if
shared?
I can. Let me see if I can share my screen.
Yes,
Are
it
you
is
able to see
clearly
my screen?
visible. Hmm.
Okay. Yeah. So today I'm going to try briefly touch upon a couple of topics, and these topics are very close to my heart, mainly because these form a lot of the basics of what we do or what we should be doing in environmental engineering. So I'll just give a brief background of how I got into life cycle assessment. Um, so I joined my PhD at Louisiana State University, and there I worked on optimization as one of my tools of working on environmental issues. Um, but after that, I went to the United States Environmental Protection Agency, and that is where I was introduced to the concept of life cycle assessment. So, life cycle assessment is a very powerful tool, mainly because it allows you or gives you a structured method of doing sustainability analysis. So I'm sure everyone in this group has already heard of sustainability. And there are many ways in which we can do sustainability for our own selves. For example, we can ride a bike or bicycle instead of riding a bus or a car. We can use reusable bottles for drinking water and not use plastic bottles. We can do many things. Uh, but when it comes to engineering, there are specific ways. Engineers need numbers, engineers need comparisons. And there are specific ways in which engineers can do an analysis of whether something is truly sustainable or not. Now, when it comes to sustainability, there are two major schools of thought. One is the engineering school of thought, and the other one is the policy school of thought. What we typically see around us are driven primarily by policy and may not be by engineering. The reason I'll give you through my talk today, and how can we analyze for sustainability for and I'll take a case study of sustainable manufacturing. The materials I will send later, along with some reading and starting materials. What I have assumed in these talks is that they are the audience does not have any background in life cycle assessment, and hopefully this will give you a primer of how and why and what we do. So that's the way I've designed these modules. Okay, so a lot of us in this group are engineers, and or have a basic degree in science, or may not be scientists at all. But how do we know where we fit in doing life cycle assessment? What we are going to learn next is, why do we need to know about life cycle assessment? The third question is what? And the fourth question is, how do we do an LCA, life cycle assessment? So these are some of the 4 questions that I'm going to answer today through this talk. So process engineering, I had a look at the list of participants, and uh, it is very interesting. It's a very interesting mix of both undergraduate, postgraduate, and professionals. So I would like to start by saying what process engineering is. So process engineering is the way in which, or the part of engineering, or uh, something that allows us to convert our raw materials into our products, and that we go through a process. Now, a process engineer may come from the domains of chemical engineering, mechanical engineering, civil engineering, or electrical engineering, but most of them have something to do with part of a process. So that's where process engineering term comes from. Now, this is what a process looks like when we design it. So these are designs that we are going with. So I'll give you this example of a corn stover process to ethanol. And this design is available in my book that I wrote for my PhD. Um, a corn stover to an ethanol process, this is a HYSYS process design. HYSYS is a computer simulation tool that allows us to design for chemical processes. So here we see in the top, we have water and biomass, which is a dry corn stover. And I'll explain what corn stover is in a little bit. Water and dry biomass comes into the process. So this becomes biomass. And then we have a separation process where we use a shredded biomass. We make it a shredded biomass, and then we have some fine particles that get out of this. We have a pumping system, and then we have this vessel for reaction, hydrolysis reaction with steam hydrolysis. Then we have a separation process here. We have a heat exchanger, and then it goes to a chemical, or enzymatic hydrolysis, where we have another breakdown of that biomass. And then we have it going into these reaction schematic, where we have a first stage reactor and a second stage reactor, where the biomass gets converted into ethanol. And then we have an ethanol separation process. We have a distillation scheme where we have the ethanol being removed in 2 different stages. And then we have a separator, a membrane separator, which gets the last bit of water out to give us our ethanol. So this is a whole schematic, and we have many different engineers, different types of engineers and scientists working on different parts of this to put this thing together. So there may be scientists who are working on the enzymes which create the hydrolysis. There may be scientists who are working on the yeast or the bacteria, which is doing the fermentation process. There are engineers who are designing the distillation tower and the columns that are required. So we have our role to play in each and every part or some of these parts of the entire process of corn stover to ethanol. So corn stover is the residue left after you use or you harvest corn from the fields. So that this process by itself looks very nice because corn stover is a waste from the field and you're converting that into a useful product. Now, ethanol is used in the biofuels industry. Ethanol is a biofuel and it is used in the biofuels industry for many purposes. Mainly, it is used as a fuel additive. There has been research done on many different kinds of ethanol in fuel blends, and I'm going to go into that. But corn stover to ethanol is a process, and this corn stover to ethanol is made, can be made from corn stover through this schematic of first a steam hydrolysis, then an enzymatic hydrolysis, and then going into your reaction scheme and then a separation scheme to get to the ethanol. Okay, so let us keep this in mind. So if you look at the overall macroscopic view of process engineers, so from the macroscopic viewpoint, we see corn stover to ethanol, which is the enzymatic hydrolysis and fermentation. And our targets would be to maximize the yield of ethanol, maximize the profit from this entire process, and minimize the waste. So you have input materials, input water, and input energy. And then you have outputs of product, co-product, and waste. And this waste can go to either air, water, soil, or other medium. So the details of the design, there is a pre-treatment of corn stover to release the sugars. So if I've seen some agricultural experts in the team, and I see that the corn stover has a two-step hydrolysis of cellulose and hemicellulose. So hemicellulose and cellulose are the two kinds of sugars. Cellulose is a 6-carbon sugar and hemicellulose is a 5-carbon sugar that is released when you do the pre-treatment of the stover. Now, then once these sugars are released, only then can fermentation of sugars happen to ethanol. And this happens through yeast or bacterial fermentation of sugars to this ethanol. Now, separation and purification of the ethanol requires distillation columns, as I mentioned, to separate it from water, followed by the membrane separation to retrieve the ethanol from the water ethanol azeotrope. But what follows this design? So we have now designed this plant, we have designed the schematic, we have done all the numbers, inputs, outputs, and everything else. But what happens, what do we do after the design? If the plant design is acceptable and the products are profitable, we do some analysis on the products and the inputs, raw materials, and we look at whether the design is acceptable and profitable. Then we select a plant site, we do detailed design, and the facility gets built. Now, I have put these as 2 bullet points, but these probably need some of the most rigorous calculations to be able to make or come to a decision that this is going to happen. Next, what happens is that once the plant is built and it has started, what others see at the plant is that there are these huge bales of corn stover coming from the farm. It gets into the plant facility, and then you have ethanol being shipped out, or trucks of petroleum being shipped out. There can be this ethanol production, just the ethanol shipping, or it can be the ethanol can be mixed with gasoline at the plant site. But this is what people see, that there are truckloads of raw material coming in and there are trucks going out of the finished product. The next question comes is, where does the stover come from? So here there are some pictures that that show you where the stover is coming from. And here we see that there are farms and fields of cornfields. And from that, we have these harvesters where we have one equipment doing the harvesting and another one is the collector. And then what is left out on the field is these huge bales or rolls, which are then collected. They may be like circular rolls, they may be square rolls or whatever, but they are collected in these equipment, in these vehicles, and they are shipped. They go to this plant site. What happens to the ethanol is that, as I mentioned, it may be ethanol in its pure denatured form, or it may be also blended with gasoline. But typically what happens is this ethanol goes to a fuel blending station. And these blending stations are determined according to the distances that you travel, and they're also more distributed in nature. And that also has gasoline coming in. So here I show an ethanol truck, and then in the bottom, the white one is a ConocoPhillips a gasoline truck. And they come to these blending stations and they get blended. Now, in the United States, in certain areas, you have these different kinds of fuel blends that are produced. So what you see in this picture is 91, 87, and 89, which are the three different types of octane numbers that are available in the United States. And you have another couple of options. This is not, these last two options are not available everywhere, but the first three options are available almost everywhere. So the first three options come with a mandate of 10% ethanol. So the United States has a mandate of blending of at least 10% ethanol in all the fuels that are produced in the country. So you have to have 10% ethanol in all your fuel blends. What you see on the right side is something that came up in the 2005 to 2015 timeframe, and this has not been implemented throughout the country. There has been a lot of discussions and policies that are going on even as of today to whether make this mandate of 15% instead of the 10%. And there are also certain vehicles that have been made that can run on 85% ethanol. So 15% E15 means 15% ethanol blended. E85 means 85% of the fuel that you're looking at is ethanol. And then this goes into your trucks, your cars, your flexi fuel vehicles. So the E15 and E85 are known as flexi fuels, and the vehicles that run them are flexi fuel vehicles. So you're able to do this, you're able to use the gasoline only after you have these blending of this 10%, or if your vehicles are specially manufactured to handle E15 and E85 fuel blends. So if you look at the overall picture of corn stover to ethanol, you have corn cultivation, you have the stover collection, you have the corn stover transport, you have the ethanol facility, you have the ethanol transport, ethanol blending with gasoline, fuel distribution, and fuel end use in cars. Now, this entire process engineers fit into ethanol facility. However, you may be fitting into any one of the other stages, but mostly process engineers are standing at a place where they can look at the facility only. And you have the inputs of corn stover, water, energy, chemicals, and enzymes. You have the outputs of ethanol, carbon dioxide, other emissions, and wastes. And you have yields, recycles, and technology. So these are what we can theoretically control as process engineers. So mostly when you are doing a life cycle assessment, you only have these few variables to play with or tweak or do differences in. And that is why it is important for us to understand the overall picture so that we understand where we are fitting and how we can control the process that we are dealing with. So life cycle assessment, what it gives is a bigger picture. The upstream and downstream effects of a process are often the deciding factors for new technology to the market. What we have realized is that may not be the best of the processes are going to be considered, and it may just very well be the upstream and the downstream effects that are deciding for the new technology to come to the market. So in case of corn stover, here these are some things that we want to point out. In case of corn stover, the transportation of stover from the field to the plant gate is expensive because of low density of the feedstock, which makes it an extremely expensive feedstock. So if you remember those bales of corn stover that are low density compared to other types of transportation, and this makes it a very expensive feedstock. The challenges in yield of sugars from the cellulosic feedstock are yet to be addressed. So if you looked at the getting the first step of releasing the sugars, we had enzymatic hydrolysis, and we also had a steam hydrolysis for getting the cellulose and the hemicellulose broken down into its sugars. And the yield of the sugars that we get from these two processes are pretty low, and these challenges are still being addressed, and they have not been addressed as of today. The ethanol federal policy, so next we come into the policy realm, where we have this ethanol being subsidized for the blenders. So if you have a plant producing ethanol, you will not get a subsidy, but if you're a blender, then you are going to get a subsidy. This federal policy has hurt the producers of ethanol very much, especially in the cellulosic or the realm of like second generation biofuels that we are talking about. Mandates are hard to meet as the cost for plant setup and operation is borne by the producer. So once you have this mandated, but you have a different policy structure, it becomes hard to meet as the plant setup and operation becomes cumbersome for some of these producers. Lastly, emission profiles for gasoline are pretty high. For gasoline and ethanol, will vary when the two fuels are considered. So, gasoline and ethanol are different compounds. Gasoline is a blend of different carbon hydrogen mixtures, and ethanol has a carbon hydrogen oxygen structure. Um, but the emissions that you get from burning gasoline alone or ethanol alone and blends are varying when the two fuels are considered, not only the fuel wise, but also the um, like the blends. The E85 would be a certain amount, but you also have to take into consideration when you're looking at the gasoline and ethanol is the fuels energy content. So gasoline and ethanol has different energy contents, and they have more ethanol is required to get the same amount of energy than gasoline in terms of weight or volume. So why do process engineers need to have a knowledge for life cycle assessment? So process engineering, as we talked about, is at the heart of commercialization of a new technology. So you need to have a process engineer to convert your corn stover into ethanol. And this is the single most important process that you cannot do away with. And it is basically very important for us to go to a commercialization. We have to understand the process and we have to understand the steps in which we can commercialize the technology. So, new technology needs the macroscopic view to make it truly viable. Biomass use is good because general consensus as carbon dioxide released from biomass but can be fixed easily over shorter time than fossil fuels. However, when we consider the biomass as a potential feedstock, we do not take into account often, I wouldn't say that we do not, but we often do not take into account the water use, the energy use, the volatile emissions that have gone into making that biomass and to convert it into the product. It is higher compared to gasoline. Maybe using biomass is not so green after all. So these are certain issues that have come up. They are not popularized because of different policy measures that the government has already taken or something. But water use, energy use, and volatile emissions is higher compared to gasoline production. So that's why we need to understand the technological gaps and where these things are possible to change. So insights from the life cycle assessment can be used for targeting the hotspots within a process. So you can identify the emissions with respect to rest of life cycle, and this can trigger the installation of better control equipment at the facility level. Governmental policies for facilities can be set based on the results of a life cycle assessment, and comparison to other competing fuels can be made. So these are some of the major benefits of having knowledge and insights from life cycle assessment. Doing a life cycle assessment can be very rigorous in its scope, and there are large groups that do the life cycle assessment. The problem in doing with a life cycle assessment, I'll come to that a little bit later, but the problem is that if you look at these different options or the different life cycle stages, there is a lot of variability, uncertainty, and differences that come up in these processes. So tackling them is very important to understand what your boundaries of life cycle assessment are. With this background, we will be now learning about the methods of life cycle assessment and perform a hands-on training of how to do an LC. I'm not going to go into the training part because it is pretty self-explanatory. And I would like to concentrate on the methods in this and let you guys use that for the hands-on training. So life cycle assessment by definition, if we are to go for the definition of life cycle assessment, there are different definitions in different realms, but here I have taken a couple of them. So the International Organization for Standards, the ones which do ISO certifications and those documentations, they define life cycle assessment as a compilation and evaluation of the inputs, outputs, and potential environmental impacts of a product through its life cycle. So if you look at life cycle assessment, it is almost unanimously used in conjunction with environmental impacts or environmental impact assessments. So life cycle assessment, according to me, is a more powerful tool than looking at just environmental impacts. But the ISO had this for inputs, outputs, and environmental impacts. And you see that here, everything, all the time, you'll see the use of the word potential environmental impacts, because the ways in which environmental impacts are determined are pretty fluid, and that's why you use the term potential environmental impacts. The industrial ecology definition of life cycle assessment is the life cycle assessment is an objective process to evaluate the environmental burdens associated with a product, process, or activity by identifying, quantifying, and assessing the impact of energy and material use and environmental releases, and to implement opportunities to affect environmental considerations. So here you see, like, what we see in a sense is that life cycle assessment is a technique used to quantify the environmental impact of a product from raw material acquisition through end of life disposition, which is also known as cradle to grave. Cradle is where we come in, and grave is where we leave. So that's also another term used for life cycle assessment. So the message that we get from here is that to do a life cycle assessment, we have to quantify inputs, outputs, environmental impacts and burdens, and then follow a product's full life cycle to make a definitive decision, and systematic procedures required for managing the vast information. So these are the three messages that we need to understand from the definition of life cycle assessment: quantify, follow the full product's full life cycle, and do a systematic procedure for managing the information. So if we look at a generic product life cycle, we have the inputs of material, energy, water to all different stages. And we have principal products, co-products, water effluents, air emissions, solid waste, and other environmental effects. And the stages of life cycle are material acquisition, material processing, manufacturing and assembly, use and service, and retirement and recovery, which after that you have to do a treatment or disposal. So in terms of methodological framework, the life cycle assessment methodology comes in 4 stages or 4 steps. You have to define a goal and scope. That is the step 1 of goal and scope definition. And this is standardized through the ISO standards. You have step 1, goal and scope definition. You have the second step, which is inventory analysis. You have the third step, which is the impact assessment. And you have the fourth step, which is the interpretation of the results. I would like to take a short, 2-minute break, and then we will continue. afford this. Okay, so I'm back. So this was one of the most important slides where we have the framework of life cycle assessment set out in front. And the goal and scope, inventory analysis, impact assessment, and interpretation are all very important stages of life cycle. According to me, the inventory analysis is the most important part of a life cycle assessment that we do, uh, not only because of um, the rigor that is involved in inventory analysis, but also it is one of the most important things that if we do not have a good inventory, then our life cycle results or assessment results are going to be flawed, and we are not going to be able to come to the real decision. And that this is also where things are very much under research scope in terms of the methodology of life cycle assessment, is how good is your inventory and how much can you um, rely upon life cycle assessment studies. And that is why the assumptions that go into inventory and goal and scope definition are very important for consideration in future purposes. So the step one, define the goal. This is going to give you the intended application of study, and this is also for intended audience. When you define the scope, keep in mind that you have to identify the product systems to be studied and define the functional unit, define the boundaries of the product system, identify assumptions and limitations of the study, and select impact categories to be included. So these are the two stages in the first step. I'll come to the functional unit and the boundaries in a few slides, but the step two is inventory analysis. This is, as I mentioned, the most important step for process engineers. And this is highly data intensive. You can or cannot choose a certain amount of data, and you may be right or wrong based on that. Detailed mass and energy balances can be performed over the life cycle. And the advantages of inventory analysis is that you measure data and define baseline metrics of life cycle processes. While some of the challenges are the assumptions made when data is not available. So life cycle assessment tools and databases. There are tools for life cycle assessment, and there are databases that can be utilized. The two databases that I mentioned here are some of the most widely available databases, EcoInvent and Gabby. EcoInvent has about 4,500 unit processes. Gabby has more than 4,000 processes. Scope-wise, EcoInvent has a better coverage of infrastructure and transport unit inputs. You have aggregation of data. Very little is there for plastics, but there is high aggregation of data for Gabby. Sources mixed, mostly from statistical abstracts, some are from industry. Gabby, on the other hand, is more direct from the industry. US coverage of EcoInvent is limited. EcoInvent was invented, if you will, in the European Union, and that's why it has most information from the European Union scope. The documentation, both of them are publicly available documents, but actually, actual information can be accessed only through their software. The sources are published and authors with contact info are included. So if you have any questions, it is not very easy to contact people, but you have the option of contacting the people. Um, Uncertainty wise, all inputs based on transparent but semi-quantitative procedure. And in Gabi, it is not always quantified. The format, these are like very different. So these are standards that are there in the world for formats, EcoSPOLD and ILCD. So those are details that we do not need to bother about much. However, the tools that allow us to access these data are OpenLCA, SEMA Pro, and Gabi. And there are mixed user bases. The interesting part of OpenLCA is that it is an open source tool. So if you have interest, you can easily go into OpenLCA and download it and look at what the data looks like, what life cycle assessment looks like. But SEMA Pro and Gabi are more commercial tools, and they are not easily available to the general public. The step 3 of the process. So we have the inventory of the processes. Now, what do we do with the inventory? So here we have step 3, impact assessment. And this converts the inventory into impact categories or mid and end points, which explain the environmental effect. Impact categories may include carcinogens, respiratory organics and inorganics, climate change, radiation, ozone layer, ecotoxicity, acidification, eutrophication, land use, minerals, and fossil fuels. So anything that you have coming out of a process would have an environmental impact. It may be in the form of the product, which later in life gets disposed and has some climate change impacts, or it may be in the byproducts that are produced, and that needs to be taken care of. So these impact categories are ways in which we can identify what the impacts are and what amount of impacts that these products have. So advantages of impact assessment are grouping of several different pollutants into a single effect for easy interpretation. And challenges are that not all pollutant effects are well known or characterized. So that characterization part is very important for impact assessment. So if you do not know the impact of a certain chemical or a certain impurity, then you are not able to do the impact assessment. And there are thousands of chemicals and thousands of impurities that can be generated. There are groups of impurities that are generated, and those like getting those characterized is the most important part. Characterized in the right manner is the most important part for impact assessment. And we have a lot of work that is going on in that area of characterization. What is the impact of a particular chemical? And only then can we go into the impact assessment total and add these different values. I'll give you an example of impact. So we all know that carbon dioxide is a global warming gas. Methane is a global warming gas, and NOx, N2O, is a global warming gas, nitrous oxide. But if you have these three global warming gases, one carbon dioxide is taken to have an impact of 1, then methane has an impact of 25 over a 100-year period. However, there are IPCC guidelines, and IPCC is evaluating these methane impacts. And in over the past couple of years, the impact of methane has been increased from 25 to 27. So that is an example where the characterization factor for methane has changed from 25 to 27 because scientists came out with this understanding that no, methane is not only 25, it is probably 27. After lots of experiments, lots of long-term studies, they have come to that conclusion. So that is an example where impact assessment or impacts characterization is important, and that is how we can get to the right type of answers. The impact assessment phase of an LCA is the evaluation of potential human health and environmental impacts of the environmental resources and releases identified during the LCI. The impact assessment should address ecological and human health effects. It should also address resource depletion. A life cycle impact assessment attempts to establish a link between product or process and its potential environmental impacts. So here you see the reason why potential impacts is important. I've highlighted potential impacts rather than real impacts. This is because the potential, as I mentioned, methane's potential impact for greenhouse gas has changed from 25 to 27. So if we are to go with absolute terms and not change them according to how science changes, that is going to be wrong. So it may change, it may increase, or it may decrease according to the scientific knowledge that is discovered. Another important point for impact assessment is midpoint versus endpoint. So midpoint reporting minimizes the amount of forecasting and effect modeling incorporated into the LCAIA. And the results of an LCIA show that relative differences in potential environmental impacts. So midpoints are if you stop at a certain level. So let's say we are looking at global warming potential or acidification potential or eutrophication potential. That is a midpoint impact assessment. However, the number of fish dying from these causes, acidification of the water or eutrophication, or the number of people dying from global warming impacts, through asthma or other issues, that the deaths or the number of losses, those are kind of the endpoint ones, endpoint impacts. The next is the how do you do the impact assessment. So here you have selection and definition of impact categories, and that involves let me see. That involves identifying the relevant environmental impact categories of global warming, acidification, and terrestrial toxicity. So if you are looking at just global warming, then you are going to select only global warming for your entire life cycle assessment. And that is where a lot of the life cycle assessments are centered around to show the global warming impacts and not the other impacts. But for a true life cycle assessment and to make informed decisions and judgments, that it is very important for us to do the entire impact categories. Classification, which involves assigning LCI results to the impact categories. Characterization involves modeling LCI impacts within impact categories using science-based conversion factors. And this is where I mentioned that things can change. Normalization is expressing the potential impacts in ways that can be compared. This is also a very important part of life cycle impact assessment. You have to then do grouping in terms of sorting or ranking the indicators by local, regional, global, and weighting, which emphasizes the most important potential impacts. And finally, you have evaluating and reporting the life cycle assessment, impact assessment results. Some of the popular life cycle impact assessment methods are listed here. Tracy 2.0 is the US EPA's method of doing life cycle impact assessment. Recipe is the European method of doing impact assessment. You also have eco indicators. A lot of these indicators and impact assessment methods came up in the European Union because they do things differently. They are really good at certain areas of environmental protection. And that's why a lot of these methods have originated from there. However, there are methods which take into account the geographical location, the things are different in different locations. So if you are trying to do an impact assessment in India, it may be different than when you are trying to do it in the European Union or the United States. So it is important to take into account those differences for impact assessment. And the step 4 is pretty straightforward, where you have life cycle interpretation and results of inventory analysis and our impact assessment are evaluated in relation to the goal and scope of the study and reach conclusions and recommendations. And with this, you identify significant issues, whether a process will be viable or not when considered on a life cycle basis. You evaluate results for completeness, consistency, and sensitivity of the data, and then you draw conclusions based on that. Now comes the important part of life cycle assessment terminology. So you have system boundary as, if you go back to the goal and scope definition, we had the term system boundary in the life cycle assessment terminology. And a system boundary is a set of criteria specifying which unit processes are to be are part of a product system. Unit process is the smallest element considered in the life cycle inventory analysis, for which input-output data are quantified. A reference flow is a measure of the outputs from unit processes in a given product system required to fulfill the function expressed by the functional unit. And the functional unit itself is quantified performance of a product system for use as a reference unit. Now, I won't spend much time here because I'm going to have examples for each of these categories. So system boundary, a system boundary is very much known to us in terms of thermodynamics, where we have the concept of a system and its surroundings, and you have a boundary around a system. So anything that crosses this boundary becomes part of the surroundings or a system, as indicated. So anything in life cycle assessment it is a set of criteria specifying which unit processes are part of a product system. So if you are considering a product, then let's say you want to do a life cycle assessment on the life cycle stages from manufacturing to retirement and recovery, or you may choose to omit the material acquisition phase depending on prior knowledge of its impacts. So, for example, you have natural gas coming into your product system, and you know that the natural gas coming in for ammonia and production, or the natural gas coming in for methanol production, or ammonia coming in for, sorry, the natural gas coming in for a fertilizer production. All of these have the material acquisition done in the same way, but the processing of the material is done differently. So you may omit the material acquisition phase depending on your prior knowledge. However, in this case, you have done the material acquisition, you have done the material processing, and these three stages may be only important for your life cycle assessment. So understanding the system as a whole and the boundary from which materials come in and energy transfer happens is very important, and that is where I draw the line, similarity to thermodynamics. The unit processes is the smallest element considered in the life cycle analysis or life cycle inventory analysis, for which input and output data are quantified. So if you look at unit operations in chemical engineering, this is the comparison that I like to draw. You have the different parts. If you have looked at any simulation software or simulation tool, then you'll know what I'm talking about. But these are figures, or like these are small units: pumps, heaters, equilibrium reactor, fixed conversion reactor, plug flow reactors, CSTRs, or whatnot. We can there is a lot of information associated with each of these unit operations, but only when we put them in a process flow diagram that it denotes the system. So only when the feed pump is connected to the mixer, or it goes into this recycle pump, and it goes for a, this is an example of a toluene, but toluene and hydrogen process, where you have benzene produced. So these are the stages, these are the units that you connect together to get from the feed to the product. Now, for life cycle assessment, this is a unit process that goes into the life cycle. So if you look at this thing, this is more of a different scale of processes, but you can have the similarities that you can draw from process flows in that you are familiar with. For life cycle assessment, the following is an analogous to the process system. So material acquisition, everything that goes into material acquisition is put into one single unit. The materials processing is the second, the manufacturing and assembly is the third, the use and service is the fourth, retirement and recovery is the fifth, and treatment and disposal is the final unit process. So each one of these are considered as unit processes in life cycle assessment, and you have a system boundary within which these unit processes exist. Now, the next definition comes to reference flow. Reference flow is a measure of the outputs from unit processes in a given product system, which is required to fulfill the function expressed by the functional unit. So I'll come to the functional unit next, but let's understand the reference flow. So reference flows connect all information from unit process to another, and this is typically based on primary product from a particular unit process. What do I mean by that? So when you have materials acquisition, you have inputs going in and outputs coming from the process, and there is one primary product from material acquisition. If we go back, I'll give an example, but each of these is connected by a reference flow. So the ones in the blue are the reference flows that connect this material acquisition to material processing to the manufacturing and assembly, use and service, retirement and recovery, and treatment or disposal. So example is when you have corn cultivation, you have 1 kg of corn stover at the field produced from corn cultivation. And you also have corn cultivated at the field, and you can have 1 kg of corn cultivated at the field, and your corn stover may be connected to the corn cultivation part. But what connects the corn stover collection to the corn cultivation is 1 kg of corn stover at the field, because that is your input required for your corn stover collection. Now, once you have the corn stover collected, you have a corn stover that needs to be transported. So there you can have 1 kg of corn stover on the truck as a unit for conversion, or as a reference flow between corn stover collection and corn stover transport. You can have 1 kilometer travel by the stover truck. You can have 1 kg of ethanol produced at the production facility. This is very relatively easy to visualize, is that 1 kilometer of stover that the truck has stover truck has traveled means that would bring in certain kgs of stover to the ethanol facility. And the thing that you convert that total kgs of stover, and you get the 1 kg of ethanol at the production facility. So that is your transformation that you require to know. And that is where the reference flow connects the information. So likewise, you have also 1 kg of ethanol on train car, 1 kg of blended fuel at gas station. All of these are your examples of reference flows that connect one unit, one unit process to another unit process. The final one is functional unit, which is quantified performance of a product system for use as a reference unit. So here you have materials, processing, manufacturing, assembly, use and service, retirement and recovery. But all of this is done for maybe, let's say, what are you trying to do from the process? Are you looking at the material acquisition, or are you looking at treatment and disposal? What is the function that you are trying to study? So typically it would be either the beginning or the end of a process that you are trying to study. So the unit that defines the function of a system that we are interested in studying is the functional unit. And this is typically based on the goal of the study. So for example, if you're looking at 1 kg fuel burnt in passenger car, that is the fuel end use in cars, and you go through all these different processes, and that gives you this 1 kg of fuel that you burn in the passenger car. So everything else that is needed to compare this 1 kg fuel burnt in a passenger car between two different processes or two different pathways is an example of reference flows, and the function that we are trying to compare is the 1 kg fuel burnt in passenger car. So, recap of life cycle assessment. So, we have systematic accounting of inputs, outputs, and environmental impacts associated with the product from a system. Goal and scope, life cycle inventory, and life cycle impact assessment and interpretation of results are the steps required in an LCA. The definition of a system boundary, unit process, reference flow, and functional units have been given. And life cycle assessment for process engineers is important to understand the big picture, to derive insights for process improvement, determine, verify mass and energy targets, and incorporate, most important, and this is according to me the most important thing, is to incorporate life cycle thinking or life cycle perspectives in sustainable design of processes. This is more important than doing the assessment itself. So you have to develop an idea or understanding or appreciation of life cycle thinking or life cycle perspectives in order to have sustainable design of a process. So the following is a life cycle assessment case study. As I mentioned that I won't go into the details of the case study, but this gives you an option of comparing methanol production routes from carbon dioxide. I'll just include some of the case studies objectives that you can look at. This is a hands-on training on how to conduct an LCA. This gives you basic understanding of system boundary, functional unit, and reference flows. You can use Excel for this case study, and knowledge of impact assessment methods is delivered. And you have familiarity to compiling a life cycle inventory, familiarity to conducting life cycle impact assessment, and results interpretation. So here, the problem definition is that methanol is traditionally produced from natural gas via steam reforming of methane, and it can also be produced via catalytic hydrogenation of carbon dioxide. CO2 is a greenhouse gas, and its consumption promises a sustainable option compared to fossil fuel-based natural gas feedstock. This problem will compare the various processes for the production of methanol using life cycle assessment and determine which process is best for the production. So goal and scope, you first define the goal and scope, that it is methanol production that you're looking at. So feedstock extraction is not very important. Methanol use is not very important. The methanol disposal is not very important. So here you immediately look at the goal and scope of the process, and you determine that the new methanol production process is your main important step. The process description for conventional process as syngas preparation, methanol synthesis. And these are some processes that give you new processes that are maybe hydrogenation processes over catalysts. And they have different raw materials, different reaction pathways. And how do you determine, and different energy uses or energy systems. So you look at the streams for various methanol production processes. This is your life cycle inventory of inputs and outputs and energy required for the process. You have environmental impact assessment with Tracy. You have life cycle impact in the categories of energy intensity, water intensity, material intensity, global warming, smog, and human health impacts. So you have this inputs identified in that manner. And then you do the characterization. So here, an example of characterization factor in the global warming category is demonstrated. So your total impact is the impact or potential impact is a sum of your characterization factors multiplied with your elementary flows. And that gives you the total, so that gives you the characterization for each individual compounds, and then when you add them up, you get the total impact from the process. So life cycle impact assessment results calculated using the previous slide gives these, and interpretation of results in terms of material intensity. You can compare the different processes based on material intensity. You can look at the water intensity. You can look at the energy intensity, and you can look at the global warming potential. Also the human health impacts and smog formation potentials. So based on the results, the conventional process is the best in all categories on a relative scale. This is your interpretation that you can get. It will be beneficial to keep the conventional processes, and improvement of other processes based on these results is desired to make them acceptable. So I would like to acknowledge that this education module has been supported through the funding from the US National Science Foundation with the award title RCNC's Sustainable Manufacturing Advances in Research and Technology. It's a coordination network. And with that, I would like to conclude the slides for the life cycle assessment part. Um, Swamiji, can we take a short break of about 5 minutes?
Hello.
Hello?
How much time do you need again?
About 3 to 4 minutes, 3 minutes. I just need to go get some water.
Oh no, that's all right. That is all right. But after that, how much time do you need? I mean,
About half an hour.
okay,
Yeah.
that's
I
all
think
right.
we had like about 2 hours.
Oh, I
So,
see. I see. Yes. No, actually, I made it as I mean, 1.5 hours. We can do one thing. Today we can finish little early. I mean,
okay.
and tomorrow you can have some little more time.
No, I mean that's fine. I
Actually,
think I have
after
covered
after
most of
after
it today.
15 minutes, I have to do a physical meeting for our ashrama, Swami
Okay,
Vivekananda's birthday. So
okay,
15
okay.
minutes you take, and but tomorrow I will be here only, so you can
Yeah,
take
so
a.
what I'll do is I'll probably then end it here today, and I'll just give you the slides for the sustainability metrics. It's not that much important as well,
Oh
like it's a
yes,
follow through of this.
okay,
But then I would like to take this time to answer any questions if anybody has any questions.
okay, that's all right. Yes, okay, no problem.
So are there any questions?
Now you take your water because.
Yeah, I'll go get my water. Hello? Yeah, I'm back.
Yes, Devalina, please continue.
Yes. So I'll just go briefly over the sustainability metrics and indicators. It won't take much time, but I'll also be sharing these slides. So if there are any
Yes,
questions,
yes,
I'll be happy.
yes. I will be out after 15 minutes. With
Okay.
that, okay. But
Yeah.
tomorrow I will be there. I mean, I don't have any such assignment.
Okay. 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 So if there are any questions on the life cycle assessment part, you can either ask here, or you can also send me a chat in the chat window, and I can answer the question accordingly as well. If not, my email is available. So if you have any questions or any comments or anything, please feel free to ask. So the next part is the sustainability metrics and indicators for sustainable manufacturing. And this one is I'll give you the overview of sustainability and how what this means, and discuss some of the metrics and indicators. So we all learn about sustainability, and we all know about sustainability, but there are certain axioms that we have come up with for sustainability. And sustainability is always about systems. It is always relative and never absolute. You have certain sustainability functions, which can be economic, environmental, and societal. The scale of the system determines the nature of the set of indicators and sustainability analysis. And indicators are not pure in the Brundtland sense, and they're often 2 or 3 dimensionals. Um, we have heard about the systems in the life cycle assessment perspective, but system surrounding paradigm in a much bigger scope is the maximum space over which the process owner has control. And in terms of sustainability, it becomes very difficult to do things because not everybody has control over each stage of a life cycle or whatever. And that is why a sustainability analysis is required, and to work with each other so that the control space is not violated. Essentially, it is an accounting of what the system is doing to itself and its surroundings in terms of environmental, societal, economic, and how these impacts can be minimized. So, this is a systems view of sustainability that was developed by Joseph Fixel from Ohio State University. And there he had a comparison between economy, society, and environment. We take economy as the economic capital, which creates value for the society. Um, the society thrives on human capital, and we all take both the economic capital and the human capital takes goods and services from the environment. So the environment is our silent provider. And then whatever we return back to the environment in terms of wastes or emissions, that almost for certain degrades the environment from its current quality. So the environment is mainly the provider, and the economy and the society balance each other in order to get their goods and services. So sustainability is a systems analysis. Systems is an entire field of learning in itself. Um, and it is comparative to a reference system. It must be based on life cycle of material. It must consider quantitative measures. And there are some critical metrics that characterize the system. And it must lead to a decision of better or worse than the reference system, preferably with a single aggregate matrix or index. So these are different scales of systems that have been defined: global systems, local or national or regional systems, business or institutional scale of systems, and sustainable technologies or sustainable product scale of systems. So different goals exist for different systems. So global systems lead to a sustainable planet. Regional systems lead to sustainable ecosystems, sustainable cities, economic sustainability, environmental sustainability, societal sustainability, and sustainable water. Institutional sustainability means we have sustainable corporation, industries, sustainable energy industries, and technological sustainability leads to sustainable products and sustainable processes. Um, so this is an example of 6R concept for sustainable manufacturing. You have remanufacture, redesign, recover, recycle, reuse, and reduce. So this is an example of sustainability in the manufacturing sector. You have traditional manufacturing, lean manufacturing, green manufacturing, sustainable manufacturing. So uh, there are different ways in which people look at these things. Um, Sustainable manufacturing processes can be defined through waste management, operational safety, personal health, environmental friendliness, manufacturing cost, power consumption. Uh, Now, metrics and indicators provide the looking glass for evaluating the sustainability of manufacturing processes. So, engineering approaches to sustainability may have impact accounting that we did on a life cycle basis. You can have analysis, which is comparative among processes or over time. So we can look at things over time, how things change. The reference system is the one to supersede or a chosen synthetic. And applicable metrics can be used in the comparative study. So here you see that there is a reference system. We talked about sustainability in the form of a reference system, and we have different options for the system. System option 1, 2, 3, up to n. And the metrics can be used to compare these different systems. In the analysis part, we have for system option 1, we have year 1, year 2, year 3, or year 4. And the metrics can be used to determine or analyze these different years. Or even for system option 1, for impact accounting, we look at life cycle stage 1, life cycle stage 2, life cycle stage 3, or life cycle stage 4, and we use the same metric to compare these different life cycle stages. Let me see if I have no. So one example for reference system would be the example that I gave in the last lecture about methanol synthesis. And you have different system options for methanol synthesis, and you compare them using metrics. The second one would be if you are producing something over year 1, methanol over year 1, 2, 3, and 4 using the traditional method. And over the years, you compare the greenhouse gas emissions and you see things are going up or down. It may be an indication that your methanol's greenhouse gas abatement system is not working accurately or adequately. Now, we do not have greenhouse gas abatement systems, but if you were to put in abatement systems, it can be for any other pollutants as well. And for the impact accounting methods, you have, let's say, the raw material acquisition, transport, and recovery, and all these stages. You compare the greenhouse gas emissions for those stages and see that is a metric that you're using to check the different stages of a system. Now, these are the 3 different aspects of sustainability. And you can have metrics which are 1-dimensional, 2-dimensional, or 3-dimensional. I won't go into the details, but just have an idea of 1D, 2D, and 3D metrics for sustainability. The examples of 1D, 2D, 3D can be capital cost or operating cost is in 1D metric. Water use, waste, greenhouse gases is a 2D metric because water use you lose both biodiversity loss and you have a operating cost loss. If you have energy intensity, material intensity, or chemical risk, those are identified as three-dimensional metrics. So if you we had a look at the life cycle assessment, but this is a common sustainability measures that lead to your sustainability design, sustainable design. So if you have a product or process from chemical and allied industries, you use a 3D energy consumption and its impacts, you use unit costs. You also have products and LCA based impacts. So these are sustainability measures, the 2D, 3D, and 1D that we just discussed about. There are some core and supplemental indicators for sustainability assessment of chemical processes, and these are a group of indicators that you probably currently use. But for sustainability assessment, you have to understand how these indicators are connected to each other and what is the best set of indicators that you need for sustainability assessment. So these are some of the core indicators and sustainable indicators, supplemental indicators. There are other organizations that have put in indicators. So this is American Institute of Chemical Engineers Center for Waste Reduction Technologies. The center has evolved into the Institute for Sustainability, and these are metrics for chemical processes. Some of them, the outputs can be of product or sales or revenue or value added. But material intensity, water intensity, energy intensity, solid waste to landfill, and toxic release are some of the basic sustainability metrics. There are also metrics for measuring the indicator. These are a list of metrics for measuring the indicator. Similarly, ICHEMI from the European Union has sustainability metrics in the environmental resources, impacts, economic metrics, social metrics. The pharma industry has eco-efficiency indicator sets, and you'll see that some of these metrics are all like overlapping between the different methods, but you'll see that material, energy, water intensities, global warming, ozone depletion, toxic release, and product characteristics and quality of management. There are some common indicators for each of these sets. BASF is a company and it has eco-efficiency indicators. Again, it uses about 6 indicators for its products. So how do we compute the indicator values? And they can be coming in from inputs, the outputs, and then you have the indicators that connect those metrics. The basic metrics are computed from data collected on the processes, which are raw materials, products, environmental releases. It is always important to express metrics in the form of an intensity, such as material or energy intensity, which makes it comparable to the metrics from another process. The secondary metrics are those which require further characterization to compute and compile several species into a single number. So for example, global warming potential is an indicator which multiplies characterization factors to greenhouse gas releases and adds these values to get a single indicator for GWP. So I gave a very brief and rough overview of the sustainability metrics. Sustainability metrics always compare options within systems. No standard metrics for manufacturing systems exists as of today. And AICHE and ICHEMI metrics are suitable for use in manufacturing systems. Again, with that, I would like to conclude. And if you have any questions, please let me know.
is open for discussion from the participants.
Any questions are fine.
Ankur, Ankur is my student, very sincere regarding joining, but I don't know
Great.
whether he is. Actually, if the speaker is very able, then generally there is no such questions because all the doubts should be dispelled by the talk.
No, I would also like to take this opportunity to thank you and also encourage students to
Yes,
consider higher education in the United States. I know, like sometimes I never thought that I would come into higher education in the United States, but um, it gives you a lot more perspective, and it also gives you the opportunity to expose yourself to diverse cultures, diverse people. I have met and worked with at least 25 to 30 different countries, people coming from 25 to 30 different countries, and that gives me a very different perspective. So I would like to encourage students to have, if you have any questions or if you have any interest, please let me know. My contact information is available. So anytime you want to have any discussion, I'm always available. So please let me know. And any guidance or career counseling that you require, given the current circumstances with COVID-19 as well as the recession that's ensuing. So if there are any ways in which you want to change things the way they are, there are options. There are options for research. Anytime you want to do anything undergraduate research or anything, just we are just a phone call away, so or an email away. So let us know, and we'll be happy to guide through these difficult times.
surely, Devalina, and also we will seriously think of the, doing something as a partnership. That is very
Yes,
much
absolutely.
necessary.
Absolutely.
That I will
I mean, there is
discuss.
no doubt about that.
Yes,
We are going through a MOU signing with
yes,
Jadavpur University, and I don't know if you know about that. So we'll
yes,
definitely look at that.
yes.
So Shayon, yeah, my email and email is available with you, sir. So if you
Yes, Shayan is about to join the PhD in
okay,
under Professor Bhattacharya and myself.
okay,
So
great,
he has completed the MTech on renewable energy.
okay,
So the
great, great.
only thing is that the Jalpur University, the admission notice is not being released because of so and so. I mean, this pandemic problems. So
Hmm.
that's why he is waiting. So the other thing is that there will be that on 29th, Sanjay Banerjee will join. I hope you know Sanjay Banerjee of City College of New York. A very, very, very senior man. Basically, he
Hmm.
is from IIT Kharagpur and long years settled in USA. Professor Sanjay Banerjee. He is the author of the book that the Safety and Hazardous Waste Management that is
Okay. Hmm.
published
Hmm.
from John Wiley. So he, I talked to him and he readily accepted our invitation. So his lecture will be on 29th. So
Okay.
and from 7 o'clock onwards. I mean, our 7 o'clock. That means in New York it is 8:30.
Yes.
So naturally, I think, if you can once join, we can have some interaction on that day.
Yeah.
I will remind you. No
Yeah.
problem.
Sure. Sure. Sure.
Okay.
Absolutely. Thank you
Okay.
so much.
Thank
Thank
you.
you.
Thank
Thank
you.
you for the
And
opportunity. And tomorrow I'll have a couple of case studies on sustainability design.
tomorrow there is no limit on time. You,
No, no, no. That's fine. I just wanted to give
because
a
I
brief.
want to do this. I am having that, but Simply, I have to go for our Swami Vivekananda's birthday meeting. So
No, no,
it
no.
is on the
That's
physical
fine.
meeting. That is on 12th January. So that planning and okay.
Mhm.
Thank you very much.
Okay. Okay.
Okay.
Thank
So
you.
I'm
Bye
closing
bye.
the meeting now. Thank you.